Fine. So these are the all about the relation. Now I will start the set. So okay. So can you hear me, because I think I have some internet problem. So my voice is clear?
Yes, sir.
Okay, fine. So now we will start the set actually, okay? And in set we will see the not the cardinality. In the next lecture we will see the cardinality. Now today we will see the countability. So what is uncountable, uncountable, finite, infinite, all of this time. So first I will do the flow chart so that it will be it will be easy to understand. So you have set. So this set can be two types of set. It can be finite or infinite. Okay. So it is a two portion. So one is finite, one is infinite. Okay. And a finite set is always countable. A finite set is always countable. And an infinite set can be both. It can be countable and uncountable as well. If you take infinite set, it can be countable or it can be uncountable. Okay. In other way, you can write in this way as well. You have set. A set can be both countable or uncountable both. So countable, uncountable both. Okay. But when you have countable, it can be finite or it can be infinite. So it has two options, finite and infinite. Okay. And a uncountable set is always infinite. So this is the chart. Okay, now I will define all of this. So what is finite, what is infinite, what is countable, what is uncountable. So first start with the finite set. So a set X is called finite if there is a bijection f so 1 to n to x for some n belongs to natural number n. Okay, and then we can write x as the set, say x1, x2 up to xn. Okay, so if x is a finite set, we can always list them as a this kind of x1, x2 up to xn, where xi equal to f of I. Okay, and I equal to 1 to up to n. So this. Now what about the empty set? So empty set cannot be write as a list, but we will always assume that an empty set is finite set. So the empty set, we denote this symbol, right? It is not phi. You should not call it as a phi. It is just a symbol of empty set. Is considered as finite set with cardinality 0. Now you can ask, so what is a cardinality of a finite set? So the number of elements of a finite set is called the cardinality of that set. Okay, so for a time being we define cardinality for a finite set. So we are not defining the cardinality for the infinite set for a time being. We will define that later. Okay, so when we define the cardinality of infinite set, then it will gives a long theory, and we will do that later. Okay, so this is the finite set. Now then, what is the definition of infinite set? Now it is simple. Now infinite set means if the set is not finite. So if the set is not finite. So that's mean if you have a set which is not finite, then we will call that as an infinite set. Okay, so that is the definition only. Now there are two types of infinite set. So first of all, countably infinite set. Countably infinite set. So that's mean it is an infinite set, but we can count the elements. So in other words, we can list the element. So what is the countably infinite set? So let X be a non-empty set. Then X is called countably infinite. So if there is a bijection from n to x. Okay. So remember how we define an countable infinite set. We define a bijection from n to x. Okay. Then we define countable set. So it is either finite or countably infinite. Okay. So if a set is finite or countably infinite, then we will call that set as a countable set. And similarly, we can define uncountable set if it is not countable. Okay. So in this way, we can define that countable set, uncountable set, finite set, and infinite set, and also countably infinite set. Fine. Now we have a simple lemma. It says that so if you have an infinite subset of natural number, okay, that one is always countable. That means if you take any subset of natural number, that is always countable. Okay. So that's mean you cannot have a uncountable subset of natural number. You cannot have that. So the lemma is every infinite subset of n is countably infinite. Okay, so that is actually the proof is actually very simple. So here we use the well ordering principle of natural number. So we will use that, and then the proof will be very trivial. So what we will do? So let x be an infinite subset of natural numbers. Okay. Now then, by the that well ordering principle of natural number, we have x has a least element. Okay, say x1. Okay, now we define f of 1 equal to x1. Now take x minus x1. Now this is again a non-empty set. Why? Because x is infinite. Now since x is infinite, so x minus x1 is non-empty, right? Now again, by the well ordering principle of n, that x minus x1 has a least element. And say x2. Okay, and then define f of 2 equal to x2 and so on. So in this way we are defining. Okay, and note that here by our construction, so by construction you can check that x1 less than x2 less than x3 x4 this. Why? Because x1 is the least element of x and x2 is the least element of x minus x1. Okay, and x3 is the least element of x1 minus x2 in this way. X3 is the least element of x1 minus x2. Okay, and so1 means now take x3, or you can say that xn plus 1 is the least element of x minus this. Okay, so by the construction we have this. So therefore, so thus we have a function f natural number to x by f of n equal to xn. And by the construction, since this imply xn less than xm, so therefore f is injective. And also by construction, for each x in x, we must have a natural number n less than or equal to x such that f of n equal to x. Okay, so this is the by the construction again. So therefore F is surjective also. So thus if natural number to X is bijective. See, we have taken an infinite subset of natural number and we get a bijection from n to x. So therefore by our definition x is countably infinite. Okay. So that's mean if you have a bijection from natural number to x, then we can say that it is countably infinite. Now we will see that actually we do not need bijection because bijection is a difficult task to find, right? Suppose you want to show that a set is countable or maybe countably infinite, then always to find a bijection is a difficult job, right? So we can reduce this one a little bit. So now we will prove that it is sufficient to find a surjective map from a natural number to x. It is sufficient to find that. Now next result says that lemma. Lemma says that the following are equivalent. And first one is x is countable and the second one is either x is empty or there is a surjective map from natural number to x. Okay, the following are equivalent. So that's mean if you want to find that, if you want to prove that a set x is countable, then it is sufficient to find a surjective function from the natural number to x. So first we'll prove that one implies two. So that is x is countable. Now since x is countable, so x is countable. So it has three cases. So first one is x is empty. Now x is non-empty finite set. And third one is x is countably infinite. Okay. Now this case is already there. We have write that either x is empty or there is a surjection. So in this case, we don't have to do anything. Now go with the second one. Now if x is non-empty finite set, that is x equal to x1, x2 up to xn for some n. Right? Now we want to define a surjective function from n to x. Now just define f n to x such that f of say I equal to xi for I equal to 1 to up to n and equal to say xn for I bigger than n or bigger equal to n plus 1. So this is a surjective function. And case 2, if x is countably infinite, then there exists a bijective f into x. So this is a surjective. So that implies f is surjective. So we are done. Okay. So therefore, if x is countable, then we have three cases: either x is empty, x is non-empty finite set, or x is countable infinite. All of the three cases we have proved which is the required one. So that's when x is, if x is empty, then we leave that. If x is non-empty finite set, then we define a surjection. And if x is countably infinite set, then we already have a bijection. So therefore, f is the surjective as well. So we are done. Okay. Now we move to the this one. So second to first. So assume that x is empty or there is a surjection, then we prove that x is countable. So ask me if you have any doubt. So 2 imply 1. Okay.
So how will we define a bijective map from natural numbers to set of integers?
Okay. So try that one. That is very simple. Um, uh, you should try that actually. So if n to z you want to define, right? So just define, say, f of 2n equal to n, f of 2n. Uh, how to define that? I want to define 2.
Okay, sir.
So maybe it will work, or you have to little bit modify a little bit.
Yes, sir.
Okay. So 0 is not coming, right? I have to just a minute. So if I take here 1, 1, okay. So take this. Then 2 will be 0. I think now it will work.
Yes.
No, otherwise modify a little bit. If this does not work, it will be something like that only. Okay. Now, right. Now
Hello,
what?
excuse me, sir.
Yes, 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 yes.
Sir, if we prove that uh, if we find a function from a set which is not a natural number
Hmm.
to another set integer, suppose the set is natural number plus 0,
Right. Huh.
and we find a map from this set to integers,
Right.
and we prove that this set natural number plus 0 is also countable,
Huh.
then we can say that the integer set is countable.
Yeah, that is fine.
Okay, sir.
Because you can prove that is by the definition as well, right? For an example, you have two set, say A and B. You already have a bijection, this, right? And you have a bijection from N to A. So both are bijection. So therefore, you can define a bijection N to A to B. So this is your F, this is your G. So F compose G is a bijection from N to B.
Yes, sir, understood.
Right. So you can always prove that. And also now onwards you don't need bijection. If you prove that only surjection from natural number to that set, then also it is fine. We just we are just proving that one. So if x is countable, then there is a surjection from n to x. Okay. Now we just prove the reverse one and we will stop today. So we will now we will prove 2 implies 1. Now if x is empty, then it is countable because it is a finite set. So we are done. Now assume x is non-empty and if natural number to x. is a surjective function. Okay. Now what we'll do, we shall find one injective function g from x to n. Okay, now how to find that? That is very simple. Now what we'll do, now since if n to x is surjective, right? So for each x, f inverse x, this singleton set is non-empty. Okay. Now we define that minimal element of this one to define this. Now define g of x equal to minimum of this set. So minimum of n belongs to natural number such that f of n equal to x. Okay. Now if g of x1 equal to g of x2 equal to say m, now that imply minimum of n such that f of n equal to x1 that is equal to m, and also minimum of n such that fn equal to x2 that is equal to m. Since this is the minimum, so f of m equal to x1 and also f of m equal to x2. So that implies x1 equal to x2. So therefore g is injective. So that implies g from x to n is injective. So that implies g from x to gx, which is subset of n, is bijective. So that implies g inverse from gx to x is bijective. Okay. Now what is gx? Now gx is an infinite subset of n, and we already proved that. We proved that in that case there exists a bijective map h from n to gx. So therefore n to gx you have a bijective h, and gx to x you have g inverse. So that implies g inverse compose h n to x is bijective. So we are done. Okay. So therefore x is countable if and only if and only there is a surjection from n to x. So from now onwards, if you want to prove that a set is countable or countably infinite, it is sufficient to find a list, or it is sufficient to find a list. The terms may be repeated. Okay, so I will continue from the next lecture. So if you have a quick question, you can ask.
Gx may be finite subset, right?
Gx, no. Here we have already proved that it is infinite, right? So finite case we have already.
In the second, we does not take infinite case. Fn to x is a surjective. We have just suppose it.
Oh, right, right. Just a minute, just a minute. I forgot that one. Right. So this is injective, right? Now here from now onward, right? Right. So here we have another case actually. So if Gx is finite, that imply x is finite. Since it is a bijection, that imply x is countable. Thank you. And now if Gx is infinite subset of n, then we already proved that. Okay, fine. So thank you for the correction. So it may happen that Gx is finite, right? If Gx is finite, then x is finite. So therefore x is countable. Now if Gx is infinite, then we do the rest. Okay, is that fine to everyone? Okay, okay, then we can stop today.